Next talk is by Professor Dutiman Sen from IIT itself, and he's going to talk on Majorana end modes, topological invariants, Floquet theory, and conductance.
Okay, so let me begin by thanking the organizers for inviting me to give this talk. So in this talk, I'm going to tell you about three different things, all related to Majorana modes at the ends of a system. So the first one is about topological invariants and then different kinds of phase diagrams that you can have for a one-dimensional system for different Hamiltonians. The second part of the talk is about some work we did when you drive the system periodically in time. So you have to use Floquet theory and you get what are called Floquet Majorana modes. And the third part of the talk is about some very recent work that we have done on the conductance through a system which has Majorana modes at the ends. Okay, so the work is done by in collaboration with several people. So Manisha Thakurati and Oindrila Deb are students here in ISC. In fact, Manisha is involved in all the different things that I'm going to talk about. Then there's Smita Visheshwara and her PhD student Ved Digotardi in the University of Illinois Urbana-Champaign. Ved now is a postdoc in Argonne National Lab. And then Amit Datta in IIT Kanpur and his student, well, master student Avishkar Patel, who is now a graduate student in Harvard University, and Krishnendu Sengupta in the cultivation of science, who is here in the audience. So the outline of the first part of the talk is, so first I'll tell you about the P-wave superconducting wire. It's sometimes called the Kitaev chain. And I'll tell you about the phase diagram and Majorana end modes for this system. My apologies to those who have heard parts of this talk before. But hopefully all of you have not seen everything here before. And then I'll tell you about what happens if you have spatially varying chemical potentials, periodic, disordered, and so on, and an interesting connection of this system which has superconductivity to Anderson localization in a normal system without superconductivity, which actually is very useful for us. Then I'll tell you about, as I said, potentials varying periodically in time, Floquet Majorana modes, and then conductance across finite length P-wave superconductor, particularly the effect of hybridization between the Majorana end modes, the effect of that on the conductance. Okay, so very briefly, a topological system is one which is gapped in the bulk. So there's a finite energy gap between the ground state and the first excited state, but there are gapless states at the edges of the system. And the number of kinds of these edge states for a given momentum, the number of edge states is quantized as a topological invariant. So the fact that it's a topological invariant doesn't mean that, means that it does not change if there's a small amount of disorder is present in the system. At lower temperatures, only the edge states contribute to quantities like the electronic transport, and so you get quantized quantities. So some examples of topological systems, the oldest example known are quantum Hall systems where the Hall conductance is quantized. Then there are 2- and 3-dimensional topological insulators. And then there's this one-dimensional system, P-wave superconducting wire, which is actually going to be the model that most of my talk is based on. So for the students, these are some general references on topological systems. Okay, so the P-wave superconducting wire is the following thing. So you have a one-dimensional chain, one-dimensional lattice, and electrons hop between the sides of this lattice. So this is the hopping term, nearest neighbor with hopping amplitude gamma. And then there's a P-wave superconducting pairing, so between nearest neighbors. So I'm assuming that the spin is polarized, or the spin doesn't play a role in this, so that's why there's no spin label. And so nearest neighbor hopping actually gives you a P-wave superconductor. And finally, there's this chemical potential on site. So very briefly, if you just take this model with all these parameters independent of n, independent of the location, then you can of course find the spectrum exactly by going to Fourier transform, and then you get a Hamiltonian K space. So you notice that this mixes up F and F dagger because of the superconductivity. Okay. So then you get an energy dispersion which is given here. And then, so there are 3 parameters, the hopping gamma, the superconductivity delta, and the chemical potential mu. And so as a function of these 3 parameters, there are certain places where the energy vanishes at certain definite values of K. Okay. So for example, if mu is plus or minus 2 gamma and K is equal to 0 or pi, or if delta is 0 and K is equal to cos inverse of mu by 2 gamma, the energy actually vanishes. So these correspond to the quantum critical lines. Okay. So here's a picture of that. So this is shown as a function of delta by gamma over here. That's the superconducting parameter and the chemical potential. So you get 4 phases. Now it turns out that 1 and 2 are topological phases, while 3 is non-topological. So, and there's a topological invariant which distinguishes between these different phases, as I'll discuss. Okay. So this is actually old stuff, so I'm just recapitulating this. So in the topological phases, there are zero energy Majorana modes at the ends of a long wire. So in phases 1 and 2, and these are separated from the bulk modes by an energy gap. Okay. Whereas in phase 3, there are no N modes. Okay. Okay. So what is the topological invariant here? So you look at this 2 by 2 Hamiltonian that I wrote down earlier, which connects modes with momentum plus or minus k. So you see that it's proportional to 2 Pauli matrices in this 2-level system. And so you can take the coefficients of these 2 Pauli matrices, sigma z and sigma y, and consider that to be a point in the yz plane, let's say. So as k goes from minus pi to pi, you get a closed curve. And so what you do is that you define an angle that any point in the closed curve makes with, let's say, the y-axis. Okay. So as you go around k from minus pi to pi, this curve, the closed curve, forms a winding number, and that's an integer. It's defined here. So this is a topological invariant because it can only change if the curve goes through the origin, 0, 0 for some value of k. And if it goes through the origin, the energy gap is 0. So that will be when we are on a quantum critical line. So as long as we are not on a quantum critical line, this is an integer, it's well defined. And we discover that in phases 1, 2, and 3, the winding numbers are 1, minus 1, and 0 respectively. Okay, so you notice that 1 and 2, the winding number is not 0. And those are topological. Phase 3, the winding number is 0, and that's non-topological. Okay, so this is discussed in many places. This is one reference where it's discussed. Now for an open wire with n sites, okay, so now we no longer have periodic boundary conditions, so there's no momentum. So we have an open wire. This is a Hamiltonian. So let's define these Hermitian operators, which are f plus f dagger and then minus I f minus f dagger. So these are Hermitian, and they satisfy these anti-commutation relations. So these are Majorana operators because they're Hermitian. In terms of these operators, the Hamiltonian takes this form. So notice that it only has couplings between A and B. Okay, there are no couplings between A and B and B. Okay. Okay, so the Heisenberg equations of motion take the following form. So because of that particular form of coupling only between A and B, the equations for B involve only A and vice versa. So now if you look at solutions with zero energy, so the left hand side is 0, then you find that there's an equation which connects only the A's at 3 neighboring successive terms together, or an equation connecting only the B's at 3 successive terms. So these equations can be solved by the transfer matrix method. Okay, so there's a reference for this here. So let's look at the transfer matrix for just the A modes. So you can write this as a transfer matrix like this, and then you find that if the eigenvalues, both the eigenvalues of this 2 by 2 transfer matrix are smaller than 1, then there's a mode which decays exponentially as you move from the left end of the system deep into the bulk. Okay, and so it's localized at the left end of the chain. Whereas if both the eigenvalues of A are larger than 1, there's a mode localized near the right end of the chain, because now the mode decays when you go from right to left. And if one eigenvalue is more than 1, the other is less than 1, then you don't have a localized mode at either end of the system. So that's the non-topological phase. Okay. Okay, so here's the phase diagram again. So just to repeat, but now in the language of A and B. In phase 1, we find that there's a zero energy Majorana mode involving A near the left end and B near the right end of a long chain. Phase 2 is the other way. And if the chain is not very long, then of course these two hybridize with each other, and the energies of these modes shift slightly away from 0. Phase 3 has no modes near the ends of the chain. Okay. Okay, so this is just to show you what these wave functions look like. So these are the Majorana modes. So on the left end you have something which only involves A, and on the right end you have something only involving B. Okay, so for some particular parameters. Okay. And this is for a 100-site system. So the 200, the label from 1 to 200 is there because every site has a and a B mode. Okay. Okay, now the Hamiltonians that we have considered so far are time reversal symmetric, which means that if you look at these coefficients of sigma z and sigma y, they satisfy these following symmetries. And therefore, this 2 by 2 matrix has the property that the complex conjugate at minus k is the same as the matrix at so H star minus k is Hk. So in general, this happens if you only have terms like I, A, B in the Hamiltonian, as I mentioned. So you can define this kind of a time reversal. It's not really time reversal, so in our paper we call it effective time reversal symmetry, where A goes to A and B goes to minus B, and you complex conjugate everything. So under this symmetry, IAB is symmetric, but if you had terms like IAA or IBB, those would not be symmetric under this transformation. Okay, so earlier we saw that there was a topological invariant which was a winding number, and it could take any integer value. So that's if you have time reversal symmetry. What happens if you don't have time reversal symmetry? So if you break the time reversal symmetry by introducing some extra terms, then the following thing happens. So if the time reversal symmetric model had several zero energy modes at each end, if you break time reversal symmetry, you find that these modes get coupled to each other and move away from 0, and you'll only be left with 0 or 1 mode at the end. Okay, so depending on whether R is odd or even, at the end when you introduce time reversal symmetry, there'll be only 0 or 1 mode. So what I'm saying is that if you have time reversal symmetry broken, then your topological invariant only has 2 values, okay, which you can call plus or minus 1. Whereas if time reversal symmetry was there, the topological invariant could take any integer value. Okay, so the invariant goes from some z valued invariant to some z2 valued invariant. The number of n modes when you break time reversal symmetry is given by another topological invariant, the z2 value invariant. So this is the sign of this coefficient of sigma z at the momentum k equal to 0 and k equal to pi. So we take the values of those two, multiply them together, and look at the sign of that, and it turns out to be minus or plus 1, depending on whether the number of n modes is odd or even, 1 or 0. Okay, so let me just give an example of a time reversal symmetry breaking system. So this is something that we presented in this paper, and it doesn't seem to have been considered by anyone else before. So this is a slight variant of the Kitaev chain where you allow the hopping to be complex. Okay, the superconducting parameter, we keep it to be real. So here it doesn't matter. If you change the phase of this, you can actually absorb that in the Fs for an open chain. But if you make this complex, then you can't actually get rid of that phase. So if W is complex and you write it as a modulus times a phase, then the Hamiltonian momentum space takes this form. Okay, so you notice that it's now proportional. This 2 by 2 Hk for plus or minus k modes is proportional to 3 different quantities, 2 Pauli matrices and the identity matrix. So as k goes from minus pi to pi, we get a closed curve in 3 dimensions, and so we can't really define a winding number anymore because it's in 3 dimensions. However, the other topological invariant, which is the sign of C0 times C pi, is still well defined, and this being minus or plus 1 differentiates between topological and non-topological phases. So here's the phase diagram for this model. So for phi equal to 0, we'll get back the old phase diagram, and then you'll see that it changes in an interesting way as you crank up phi. Okay. So here's the phi equal to 0 model. So you have these three phases, 2 topological and 1 non-topological, and as you increase phi, lots of things happen. So first of all, these 2 red lines, which are quantum critical lines, come closer to each other. This line in the middle sort of opens up, okay, and so on, until you get to this point where phi is pi by 2, which is the maximum value of phi that you can get, where these 2 phases 1 and 2 have completely disappeared. Now this phase, blue phase that you have, it's a very interesting phase. It's completely gapless. So everywhere in this phase, the energy vanishes at some value of k. So this is kind of reminiscent of the Kitaev model in 2 dimensions, where you have a gapless phase where the energy vanishes at certain values of k. But I think never seen a model like this in 1 dimension, where you have a continuous region in parameter space where you have a gapless phase. Okay, so that's one of the interesting things that we found when you break time reversal symmetry. Okay, now the next thing to look at is what happens if the chemical potential varies in space. So we'll take the chemical potentials to vary and keep W and delta fixed. So W is the hopping, which was called gamma earlier. Sorry about that. Anyway, we're going to set it equal to 1. So now you introduce a certain diagonal matrix, and then you find that you can do a similarity transformation where this transfer matrix, where you have the superconducting parameter delta, is related by this similarity transformation to another transfer matrix where delta is 0. So what this tells you is that this superconducting system actually is equivalent under a symmetry transformation to something which is a normal system without superconductivity. Okay, so then if you just look at, we just want to see the condition that the larger eigenvalues of this should be both greater than, sorry, the two eigenvalues should be both greater than 1 or both less than 1 to get Majorana modes. And so if you look at the logarithm of the magnitude of the larger eigenvalue, this is for the superconducting system, it's related to the largest eigenvalue of a different system which is normal plus something which has to do with this superconducting parameter. Okay, so the boundary between topological and non-topological phases is where this is 0, and so we have this relation between superconducting and non-superconducting system. So this is the relation that I mentioned earlier. The problem of Majorana modes of this system can be related to Anderson localization of a normal system. There is also duality in delta. You can relate the properties of the system for delta less than 1 to delta more than 1, which is useful to look at the interface diagram. So, but I won't get into this. Okay, so let me show you the topological phase diagram for 4 patterns of this chemical potential. So period 4, chemical potential varying in this way, quasi-periodic where it's varying as with the position label n as a irrational cosine of an irrational number times n, box disorder where it has a uniform distribution, and a Lorentzian disorder. So it turns out that the cases A and B and D can be solved analytically because of this mapping to the Anderson localization problem, whereas case C we studied numerically. Okay, so here are the phase diagrams. So I'll just show you very quickly. So in this diagram, T stands for the topological phase where you have Majorana modes at the ends of the system, and N stands for the normal non-topological phase. So this is for the period 4 case, this is the quasi-periodic case, this is the box disorder, and this is the Lorentzian disorder. Okay. So I won't, let me not dwell on this. So this is just an example of the kinds of diagrams that you can get using the methods that I've told you about. Okay. So these 3 cases we got analytically, and this case we had to get this numerically. Okay. So this is just from the transfer matrix eigenvalues being more than 1 or less than 1. That's the only criterion we use to distinguish between topological and non-topological phases. Okay, so the summary of this part of the talk is that one-dimensional systems of electrons with p-wave superconductivity can have zero energy Majorana modes at the ends of a long chain. The number of such modes is given by topological invariants. If there is time-level symmetry, the topological invariant is z valued, it's a winding number. If time-level symmetry is broken, then it's z2 valued, it's plus minus 1. And for spatially varying chemical potentials, the presence of these Majorana modes can be related to the Anderson localization problem for a normal system. Okay, are there any questions for this part? Okay, if not, let me go on to the Floquet problem. So here I'm going to consider what happens if the chemical potential is varied periodically in time. So this is an interesting area which has developed quite a lot in the last few years. There was an important paper by these people in Nature Physics in 2011 where they studied what happens to graphene, I think, if you apply if you perturb the Hamiltonian by a term which varies periodically in time. So we are going to do the same kind of thing for our p-wave superconducting wire. Okay. So we saw earlier that if these parameters are all time independent, then you can have either topological or non-topological phases. Now what we're going to do is we're going to vary, let's say, the chemical potential. It doesn't matter, you can vary any one of them, but let's say you vary the chemical potential periodically in time and see if this can generate n modes. And what we'll find is that it can actually generate n modes even in a system where the time independent part of the Hamiltonian has no n modes. So just the periodic driving can take you into your topological phases. Now we looked at 2 different kinds of periodic driving. One is this delta function, which I'll talk about in detail. So here, after every time period capital T, you give a kick to the chemical potential. The other thing that we studied is when you have a sinusoidal driving. So mu is some C0 plus C1 cosine omega t. But this case is easier to study both analytically and numerically. So let me just show you the results for this. Okay, so Floquet theory goes like this. So you have this time-dependent Schrodinger equation that you have to solve, whose eigenvectors and eigenvalues you have to find. So we define the Floquet operator as this kind of symmetrized product. So the Floquet operator basically just time evolves the system by one time period, capital T. Okay, and there are certain advantages to using a symmetrized product. So the wave functions must be eigenvectors of the Floquet operator, and because this is unitary, the eigenvalues must be pure phases. Okay, so we will find this numerically. If you write this theta as minus epsilon t by h bar, this epsilon is sometimes called the quasi energy in the literature. Okay, so the Hamiltonian for an n-side system is here. As I said, this mu is going to vary with time. This can be written in terms of Majorana fermions, f plus f dagger and f minus f dagger. And so you can write this in the Majorana language. This becomes a 2n by 2n dimensional imaginary antisymmetric matrix. Okay, so the Heisenberg equations take the following form, and then you can find the Floquet operator as this time ordered product in time of the exponential of this matrix. So there are some general properties. You can show that the eigenvalues of mu u, the Floquet operator, will generally come in pairs, plus e to the power plus minus I theta. If you have a single mode at the end of a long chain, then it must have eigenvalue plus or minus 1. Okay, so the n modes here are special in the sense that they have Floquet eigenvalues equal to plus 1 or minus 1. So that's the equivalent statement here to the time independent Hamiltonian having Majorana n modes with eigenvalue 0. Also, if it's really a topological mode, then these Floquet eigenvalues plus minus 1 should be separated from all the other eigenvalues by a certain gap in this parameter theta. Okay. So if you plot the eigenvalues on a unit circle, you should find the theta equal to 0 and pi have some isolated modes. There's another way of distinguishing numerically from these n modes and between the n modes and all the bulk modes, which is the inverse participation ratio, which is the following. So of course the eigenvectors that you find numerically are correctly normalized. The inverse participation ratio is defined as the sum over sigma, this wave function to the 4th power over all the sides. Actually we started calling this inverse participation ratio and then find in the literature that everyone defines the inverse participation ratio as 1 over this. So maybe we should call it the participation ratio. But we are stuck with this in our papers now. So you can easily see that if the psi is spread over L sides, then the normalization tells you that mod psi squared is 1 by L, and so the inverse participation ratio is 1 by L. So the more localized a state is, the larger is the inverse participation ratio according to this definition. Okay, so there are 3 methods for detecting n modes that we have used. One is that the eigenvalues must be close to plus or minus 1, the Floquet eigenvalues, and they should approach plus minus 1 as the system becomes longer and longer. They must differ from all the other Floquet eigenvalues by a finite gap, and the inverse participation ratio must be much larger than for all the other eigenvalues. Okay, okay. So this work is described in this paper. Okay, okay. So here's an example of inverse participation ratios. I think it's actually nicer to call this plot this except rather than its inverse. So you can see that there are 2 modes for which this has a very large value compared to all the other modes. Okay, so these are the 2 n modes. So here I'm just showing you the inverse participation ratio. I'll show you the wave function next. So notice that we are using mu equal to something of this form, 2.5 plus something times the delta function. So it's always bigger than 2 at all times, and so it's in the 3rd phase according to the time independent Hamiltonian. So it's in the non-topological phase at all times. So yet you're getting these n modes in the system. Okay, so here's an example of those 2 modes which had very large inverse participation ratio. So one of them is at this end, the other is at that end. And once again, in this system, these comprise of only the A modes, and these comprise only of the B modes. Okay. And the Majorana modes, the wave functions are real. Okay, so then we studied the variation of the number of n modes with the frequency omega, and here we found a very interesting thing, which is that, so there are, as you know, 2 kinds of n modes. They can have Floquet eigenvalues equal to plus 1 or minus 1. Okay, so let's plot the number of modes with Floquet eigenvalues plus 1 and minus 1. Let me call them n plus and n minus. So you discover that these vary with the frequency. At very small frequency, both of them become very large. In fact, they seem to grow without limit. So you have this strange result that if you go to very low driving frequencies, you can generate any number of Majorana n modes. Okay. So is there a topological invariant which can predict the number of n modes with Floquet eigenvalues plus minus 1 in this case? And the answer is yes. So this is how it works. So we find a Floquet operator for each momentum k, well, k and minus k, and it takes this form. Then you can combine these 3 exponentials into a single exponential. So once again you discover that for this system, which happens to have time reversal symmetry, you get an exponential of something which is only the sum of two Pauli matrices. So once again you just have two coefficients which are functions of k, and you can okay, there's some technical things here. So you can find that this object, this Floquet operator as a function of k, can be equal to plus or minus 1 only if k is equal to 0 or pi. So it can't be equal to plus or minus 1 at any other value of k. Okay. And at plus or minus 1, this is at k equal to 0 and pi, it's equal to plus or minus 1 only at these frequencies omega. Okay. So we actually have an analytical expression for the frequencies where this Floquet operators become plus or minus 1. So once again we have this interesting bulk boundary correspondence, that we have found this object in the bulk, okay, because it needs a periodic boundary condition k and everything. We find the Floquet operator there, and then we say that let's look at when this is plus or minus 1, and then we find that it tells you certain frequencies, which are the frequencies where when you drive the system an open chain, you discover that Majorana n modes appear or disappear. Okay. So here's okay, so there's a closed curve in two-dimensional space, and if you look at the winding number of this curve, it exactly matches the number of Majorana modes at each end of the system. Okay, so there is a function of omega, and you find that as you decrease omega, you actually get a very large number of Majorana modes. In fact, if you go to really small values of omega, this number of modes actually increases without bound. It's very peculiar. You can get any number of Majorana modes. Okay. Also, the interesting thing is that as you change omega, Majorana modes can either appear or disappear. It's not that they monotonically keep increasing as you go to small omegas. Okay. So here, extra mode has appeared, and then some other mode disappears, and so it sort of does this. Okay, so this was so this winding number actually tells you the total number of Majorana n modes in this problem. It doesn't distinguish between Majorana modes with Floquet eigenvalues plus 1 and minus 1 separately. So then we wanted to find a better topological invariant which can tell you the number of modes with Floquet eigenvalues plus 1 and minus 1 separately. Okay. And we found that. So this is something that so you look at these Floquet operators for k equal to 0 and pi, and demand that it should be 0. This exponential should be 0 or pi, so that you can get Floquet eigenvalues either 0, plus 1 or minus 1. And it gives you a certain condition on the frequencies at which these eigenvalues can be plus or minus 1. And then you discover numerically that at these values of omega, given by this thing being equal to some multiple of n, some integer, Majorana n mode with Floquet eigenvalue can either appear or disappear. So that is still a little bit of an unsolved problem which we have not managed to sort out. We know that this gives you the values of omega where something will happen to the Majorana n modes, but we don't have a way of figuring out whether it's going to appear or disappear. Okay. Okay. So what we do is that, so you have these two functions, okay, one for k equals 0, one for k equals pi, which are functions of omega. And so I plot these as a function of omega. So I think I don't know which one is b0 and which one is b pi. So one of them is the red line, the other is the blue line. And as a function of omega, so every time this curve crosses an integer, you find that a Majorana mode appears or disappears. Okay. And so you can see that as you go to very low values of omega, and the number of integers between these two lines, so in the yellow region, the number of integers there is the total number of Majorana n modes. So as you go down to very low values of the frequency, the number of Majorana n modes increases indefinitely. Okay. Now this is of course an ideal system, and it would be shocking if you really had a way of producing a huge number of Majorana modes. So a lot of these things break down if you include things like finite temperature, noise, and so on. So we have studied that a little bit, not in great detail. So I'm not going to discuss that here. I can talk about it later if somebody is interested. So this increasing number of Majorana modes is really for this ideal system where we ignore thermal fluctuations and disorder. Now the same kind of thing happens on a two-dimensional system. Okay. Yeah. Yes. So actually, if you take a time-independent Hamiltonian where you allow for long-range interactions, yes. then you can have any number of Majorana modes. Yeah. Yes, yes. So we have, I didn't show it in the previous work, we have long range interactions time independent where you can have any number of Majorana modes. So in some, you're absolutely right. So in some sense this Floquet driving is actually effectively coupling sites very far from each other. Yeah. No, this is a very funny system, right? It is a periodic delta function kick. So the chemical potential is constant, and then at one point there's a delta function kick, and then there's a constant. And the time between the two kicks is going to infinity as omega goes to 0. So it's not a uniform shift. Yeah, for that you don't get such a huge number of Majorana modes. You can get multiple Majorana modes there too, and we found that, but not such a huge number. So there's something funny about this periodic kick. Okay, so very briefly for, yeah. So the new invariant consists of the following. So it's a complicated kind of invariant. So we are saying that you take these two quantities and plot those as functions of omega. Okay, and so in this plane, these quantities as a function of omega, the invariant is how many integers are there between these two curves. That's the invariant. Okay, and the only way that invariant changes is if one of these curves goes through one of these integer values, and that's where a Majorana mode appears or disappears. That's also the point where you find that if you look at the Floquet eigenvalues, remember I said that they have to be, the ones at plus minus 1 have to be separated from all the others by a gap. That gap closes when you go through one of these points. Okay, so it's very similar to going through a quantum critical line, except that this is all for a time dependent problem. So here's the Kitaev model which you have heard about in the last talk. So it's got spins on a honeycomb lattice with highly anisotropic couplings between nearest neighbors. And we give periodic kicks to, let's say, one of the three couplings. So there are three couplings, J1, J2, J3. You can pick any one of them, and you give periodic kicks to that. And you discover that this generates edge states. So for example, if you take a zigzag edge state for a system, you get these extra states which live at the edge. Now in this case, of course, because this edge is one dimensional rather than a single point, these states have a momentum. Okay. There are also armchair. There are also edge states at armchair edges. Okay. So this is there discussed in this paper, and it turns out that you can understand where the frequencies at which the Floquet modes appear or disappear in this problem also by mapping this to the previous one-dimensional problem. Okay. So this is how it goes. So for a Majorana edge mode with a momentum k along the edge, you find that you can map it to the previous problem of the p-wave superconducting wire with parameters in that one-dimensional model which are functions of k. Okay, and so by using the analysis, the previous analysis, you find that Majorana edge modes with Floquet eigenvalues -1 to the n should appear or disappear at these frequencies, where now these frequencies also depend on this k, the momentum of the edge state. Okay, so here is a comparison. So the blue points are the points that were found numerically where there are Majorana modes at the edges of this Kitaev model, and these red lines are the lines that you get by saying that this omega k is of this form where n is an integer. Okay, so you get these different lines corresponding to n equals 2, 1, 0, -1. So you find that the Majorana modes indeed appear or disappear exactly at these lines. Okay, so there is this white region here where there are no Majorana n modes. Then there are these other regions. What's not clear from these blue points is how many Majorana modes are there, but we checked that if you cross this line, the Majorana modes, number of Majorana modes increase or decrease by 1. Okay, so there's perfect match between the analytical predictions of the frequencies at which Majorana modes appear or disappear and the numerical results. Okay, so to summarize this part of the talk, the Hamiltonians varying periodically in time can generate Majorana n modes even if the time independent part of the Hamiltonian is in a non-topological phase. The Majorana modes have Floquet eigenvalues equal to +/-1, and they're separated from all the other eigenvalues in the bulk by a gap. And the Kitaev model on the honeycomb lattice can develop Majorana edge modes when one of the couplings is varied periodically in time, and this can be completely understood analytically by mapping it to the p-wave superconducting wire. Okay, so the last part of the talk, so this is some work that we have done very recently about the p-wave superconducting wire So this is of course a very, very well studied problem, and this has even been kind of experimentally realized, and there was all this excitement about possible detection of Majorana modes. So the only new thing that we have to add here is that we decided to take this simple model and find as many things as possible analytically. Okay, so here's a normal metal superconductor, normal metal system. So superconductor is in the middle, and it's a p-wave superconductor. Later I'll tell you how you can actually produce this model experimentally. So there's a way of getting this from a more microscopic model, which I'll discuss later. Now in terms of electron and hole fields C and D, the Hamiltonian takes this form. So this coupling C dagger delta x D plus D dagger delta x, this is the p-wave coupling, right? So this is proportional to the momentum, and the amplitude of this is delta, and mu is the chemical potential as usual. We also allow for barriers of some strength lambda at the two junctions between the normal metal and the superconductor, because that's really there in the real systems. There's a tunneling barrier over there. Now there are two kinds of currents, it turns out, in this system. There's a particle current which doesn't distinguish between electrons and holes. So the particle current corresponds to a particle density C dagger C plus D dagger D. And then there's a charge current which corresponds to a charge density which is C dagger C minus D dagger D, which is the physical charge. But both of these currents have to be conserved, and these imply the following matching conditions at these two junctions, normal superconductor junctions. So here's a bunch of matching conditions which involve all these parameters, this barrier lambda, which leads to a discontinuity in the first derivative. Then there's the superconducting parameter delta, and so on. The wave functions themselves are continuous, but the first derivatives are discontinuous in this particular way. The conservation of particle current implies the following, that, okay, so I had these symbols earlier. Let me explain now what they are. So you have an electron coming in from this side, number one side. Then you can have a normal reflection of an electron. You can have an Andreev reflection of a hole. Yeah, this arrow should be pointing the other way actually. Then you have a Andreev, you have a normal transmission, and then you have an Andreev transmission. So the sum of these four amplitudes squared should be 1. And then the differential conductance from lead 1 to lead 3 is the difference of the normal and Andreev transmission probabilities. And there's also conductance from lead 1 to the superconductor, which is given by twice E squared by H times the sum of the two Andreev processes, Andreev probabilities. So this process is because of a Cooper pair formation. So when an electron gets into this superconductor, one thing that can happen is that there can be an Andreev reflection, and to compensate for charge conservation, a Cooper pair is formed here. And that Cooper pair goes into the superconductor and then eventually goes away into the lead connected to the superconductor. So that's the Cooper pair conductance. So there are two kinds of conductances, 1 to 3 and 1 to 2. Now the spectrum, so what we're going to do is understand these two conductances as a function of the different parameters of this model. The spectrum in the superconductor, you can solve this very simply. It has a gap from minus delta to plus delta, and you discover that the conductance within this gap, the sub-gap conductance, shows a peak at the energy of the Majorana n modes. Now for a very long superconductor, the Majorana n modes lie at 0 energy, so you get a 0 bias peak. But if the length of the superconductor is finite, the two Majorana modes hybridize and the peak shifts away from 0 energy. So take an idealized case. Suppose I just take a superconducting box. Okay, so forget about the normal metal leads. You just have an isolated superconductor. So that means the barriers are infinitely large between the superconductor and the normal metal. Then this is an analytical expression for the Majorana modes. Okay, so you see that the energies, the energy lies within the gap. So this is always between plus or minus 1, and it has this following variation with the length of the superconductor, the Fermi wave number, and this superconducting coherence length, which is a function of delta, the energy itself, and so on. Okay, so this has to be solved self-consistently. So here's the kind of picture that you can get. So you find that there are three regimes basically. Okay, one is when the wire length is much less than the coherence length of the superconductor. So then you actually get no Majorana modes in the middle. So this is like it's just like a ordinary dot, and you get resonances in the conductance only for certain special values of kf L equal to some multiple of pi. So this is like a standard resonance that you see in quantum mechanics normal system. If the length is comparable to the coherence length, then these Majorana energies, they oscillate, and also they decay exponentially with the increasing length. So since we are just showing a little interval in L, you can't see the decay, but if you stretch this out, you will actually see a decay. Eventually, when the length of the wire becomes much bigger than the coherence length, then this decays to 0. So then both the Majorana energies plus minus E just sit at 0 energy. Okay. So you have these three patterns depending on the relative ratio between the length of the superconductor and the coherence length. So what you find, not surprisingly, is that the conductances exactly track these patterns. Okay. So the conductance, this is the conductance from wire 1 to wire 3, normal metal, and this is from wire 1 to this superconductor. So you see that there are these peaks in the conductances which are exactly at the points where the Majorana modes are. So this is for the case of a very small length. So here you get peaks only at special values of the length which correspond to these values. Okay. Here you have these patterns which are there, so they are oscillating, and they are oscillating with the length as you vary the length. And then finally, when the length is very large, you get this zero bias peak exactly at 0 energy, independent of the length. Okay. So that's one of the main things about this work. We also studied what happens if delta changes sign inside the superconductor. So let's imagine that there's a situation where this P wave amplitude changes sign somewhere inside the superconductor. Then you discover that there are actually two more Majorana modes which appear there, and they don't mix with each other. This is because of this effective time reversal symmetry that I talked about earlier. Okay. The Hamiltonian only has IAB terms, and so as long as these ends of the wire superconductor are very far away, these two don't talk to each other, they don't hybridize with anyone, so they just remain at 0 energy. Okay. So one of the questions we asked is whether these two will have any effect on the conductance across the system. Okay. So we find that basically they have no effect. So this picture is more or less exactly the same as the earlier picture. The earlier picture was where delta had the same sign everywhere in the system. Here delta has changes sign at, let's say, 3/4 of the way into the superconductor. They look exactly the same. So essentially the two Majorana modes inside the superconductor seem to have no effect on the conductances. This is possibly because we only have leads at the ends, not in the middle, right? So these normal metal leads basically don't sense these Majorana modes in the middle. If you had a third lead which touches the superconductor in the middle, then of course the conductance there would be really affected by these extra Majorana modes. So it's just our setup which somehow seems to be insensitive to these Majorana modes inside the bulk. We also looked at the effect of interactions. How much time do I have? Oh, okay, that's fine. So we looked at the effect of interactions. Specifically interactions between the electrons inside the superconductor, if there are such interactions. So this can be studied using bosonization and a renormalization group analysis. So the bosonized Hamiltonian takes this form. So there are two bosonic fields conjugate to each other. Okay, so I'm just using a few things from bosonization. Theta and phi are the two bosonic fields. Then there is a velocity parameter, and then there's a Luttinger parameter k, which is sensitive to the interactions. So this Luttinger parameter is less than 1 if the interactions are repulsive, more than 1 if they're attractive. It's equal to 1 if there are no interactions. The last term, which is proportional to sine of 2 root pi theta, it turns out, is related to this superconducting pairing delta in a certain way. Now there is a parameter A0 which I put in here, which is the microscopic length scale. So if, for example, it could be the lattice spacing, or it could be, if you had a continuum model, this would be the distance nearest neighbor spacing between the particles. So that's the microscopic length scale. Then what we are going to do is that we are going to allow all these parameters to flow due to interaction. So there will be RG equations for these parameters. So even A is allowed to flow in this way. So A is like the RG length scale, and the superconducting amplitude is also going to flow, and this delta, which is the physically observable superconducting pairing, is related to this parameter in the Hamiltonian in this way. So capital delta is small delta over A. And then there are also these barriers of strength lambda at the two ends of the system. So these satisfy the following RG equations. So the Luttinger flow of the Luttinger parameter is there only because of the superconducting term. The superconducting term itself flows in a way which depends on the Luttinger parameter. So this is all written down to lowest possible order. And these barriers also flow in this particular way. Okay. So notice that this k and delta, these are bulk parameters, so they are not sensitive to the barriers at the end. So the RG equations for k and delta don't depend on lambda, but the RG equation for lambda depends on k. Okay, so that's usually what happens when you have both bulk parameters and boundary parameters. So the boundary parameters, RG equations depend on the bulk parameters, but not vice versa. Okay, so here's the effect of interaction. So these are just some plots for two initial values of the interaction parameter, 0.8 on this side and 1.2 on the right hand side. So the I don't expect you to follow too much from these plots, but the basic point is that the superconducting region has a length L, and what you have to do is you follow these RG flows and go up to this final length L, and at that point if the value reached by delta satisfies this condition that L is much bigger than 1, then it means that the Majorana n modes don't hybridize, and you'll get these Majorana n modes, they'll survive. If the value of delta that you reach at that length scale satisfies L delta is less than or order 1, then the Majorana modes will hybridize strongly and maybe they'll disappear. Okay, so that's the information that RG flows. Okay, so you're supposed to follow these RG flows, get the final value of delta, and then put it back into that earlier plots of the conductances and see where you sit on those plots. Okay, so that's what you can do from these RG equations. Yeah, sure. Yes, I didn't put it in the Hamiltonian. You're right. So I should put two extra terms in the Hamiltonian, which are at the ends of the system, x equals 0 and L. Okay, so you get a term like cosine phi at the ends of the system, which is proportional to lambda. No, so that's what I said. Because this lambda is only at one point in the system, it doesn't affect the RG flow of k and delta, which are in the bulk of the system. Yeah, so boundary terms don't affect the flows of the bulk terms. By the way, the velocity v also flows under RG, but that we have ignored in these equations. So all the parameters flow in the Hamiltonian. Okay, so now let me tell you about an possible experimental realization. So this is actually taken, sort of motivated by this paper, which is also the paper which first discussed this RG calculation that I described to you. So there are various components in this. So they start with a wire which has a Rashba spin orbit coupling. So it's proportional to the momentum along the wire times one of the spin components. So it's got this Rashba spin orbit coupling. Then it's also placed, this wire is also placed in a magnetic field with a Zeeman coupling Z, and so this should be in a different direction. So in the Z direction, which is orthogonal to the Rashba direction. And then it's also in proximity to an S-wave superconductor with a pairing delta S. Okay, so you need these three ingredients. So the original Hamiltonian with these three ingredients looks like this. Okay, so here's the usual kinetic term, the spin orbit coupling, the Zeeman coupling, and this S-wave superconducting coupling. So then what they show is that for a certain range of parameters, this is equivalent to a spinless P-wave superconductor, where the P-wave pairing is this. Okay, so you see that it is proportional to the Rashba coupling, proportional to the S-wave superconducting coupling, and inversely proportional to the Zeeman coupling. Okay, so this is the mapping of a kind of realistic model to the P-wave superconducting wire that we have been using throughout. Okay, so now based on this, we have proposed a very simple way of realizing a model in which delta changes sign somewhere inside the superconductor. And we hope this works. If you have any criticisms of this, let me know. So the idea is that if you have a straight wire, then this delta, which is given by this, will have the same value everywhere. If you take a wire which is bent, completely bent by 180 degrees, then delta will have opposite signs on the two sides. Simply because it's proportional to alpha r times the momentum along the wire. So the wire is, in this bent case, the wire is, let's say you're starting at minus infinity here, x is increasing, going to 0, and then going to plus infinity there. So effectively the direction of your momentum has changed. So we believe that this should be enough to change the sign of delta. Okay.
It doesn't depend on how you're creating the delta. So for example, if a wire is sitting on a superconductor, which is the way it is often done experimentally,
right,
and would
Yes, it would. So the assumption is that so the Zeeman field is perpendicular to this plane in the z direction, and the Rashba spin orbit coupling we are assuming is in the plane x, which is perpendicular to the wire. Okay, so essentially this direction of the wire is the y direction, and x is perpendicular to that in both parts of the wire. Okay, so
This is a wire that's kind of spontaneously superconducting, or is the superconductivity by proximity effect?
or the superconductivity is by proximity effect. So yeah, so the S wave term in the wire is because of the proximity to the S wave superconductivity.
But then how do I know that, why is the top half of the wire different from the bottom part, I guess? Let's say like it's observable, right? Whether
Oh, so the idea is, so the proposal is you just take a bent wire, which is bent by 180 degrees, but yeah,
for example, if I cut the bend, let's say I cut that left part,
yes.
then why is delta different on the top than on the bottom? If
Okay.
they're on the same substrate.
Okay, so if you just cut this, so then you get two independent wires, and then of course there's no way of fixing delta. You can actually make a unitary transformation to change the sign of delta.
Right, because the delta is basically free, but you think that the leading Josephson coupling, which would line them up to be the same horizontally,
Yeah.
would line them up to be opposite. So it has to do with the coupling across the.
Right, and it's also important that these are connected to each other. So the same electron which goes this way on the lower part and then goes back the other way in the upper part. And so that electron knows that the deltas are different on the two halves. But if you have two separate wires, then I can do independent unitary transformations on the two parts and make delta have the same sign in both. It's kind of ill-defined. So that's like your, basically delta has to go through 0 there. Yeah. So there's a little patch in the middle where, so it's like an impurity. This is Joel's question.
It's more a question about something about the barriers. What's picking the phase arrangement between the top half and the bottom half, right? I mean, it is a Josephson coupling through the barrier or something. That is, you need the green part. If you didn't have the green part, as you say, the phases would be arbitrary. So it's kind of a question about the microscopics of the green part.
That's true. No, but the green part basically just connects these two, and it tells you that the so basically if an electron had to go through this entire wire, its momentum would have to flip when it goes through this green part, and essentially that's what changing the effectively changing the sign of delta, because so the momentum shows up there in the spin orbit coupling, the Rashba spin orbit coupling. So if the momentum is flipping sign, then that effectively changes the sign of delta.
That's what I agree with. The challenge is whether a high Josephson barrier actually always flips K. But I think that's
Okay, all right. Okay, Sujit.
You can write delta in terms of sine function, then that problem will be solved. You can express
Yeah.
the sine function in terms of theta function.
Yeah.
And then
No, but the question is really an experimental question. Is what exactly goes on here? So the only way we have of modeling this is modeling it like an impurity. This is what we have done actually in our paper. We actually put an impurity there and see what happens, and we find that you get two Majorana modes. But that's the important question: what happens there? Okay. Yeah. Okay. So that's a proposal of getting systems where you have a constant delta throughout, and a different system where delta changes sign at some point. Okay, so I'll just summarize this part. And so what I've said is that Majorana modes at the ends of a P-wave superconducting give rise to peaks in the differential conductance. This is of course very well known. What we have done here is to show that for a finite length superconductor, the modes hybridize, and we have found an analytical formula for these energy splitting from 0, and shown that the conductance peaks at those new energies plus or minus E, and the splitting oscillates and decays with increasing wire length. And then we have shown that at least within this geometry, if the P-wave pairing changes sign somewhere inside the superconductor, two more Majorana modes appear there, but these have very little effect on the conductances, at least in this geometry, where you have normal metal leads only to the ends of the superconductor and not in the middle. Okay, and these are all the references for the different parts of this talk. Thank you.
Any questions?
kindly show the slides of Floquet operator.
Floquet operator. No, they don't. So H naught is the unperturbed part. So H naught is it has this, and the C0, the constant part of that, and the V naught is the oscillate, the delta function kicks in that. So they don't commute with each other. In particular, this doesn't commute with this term, right? Because there's a total fermion number, and this doesn't conserve fermion number. So that's why that's really what makes the problem complicated. You have to write them in 3 separate parts, and then you have to combine the 3 into one exponential.
Any other question? We had a few questions during the talk also. So if not, then let's thank the speaker and all the speakers of this session.